Natalie, there we go. I was just going to ask you if you were going to be recording. Thanks a lot, Natalie. All right, welcome everybody to this DesignSafe webinar. I'd like to thank all of you for being here today to hear from our speakers. The title of today's presentation is a Jupyter/TAPIS workflow for processing, visualization, and analysis of experimental and field wind data. And the presenters, originally John Paul Pinelli was going to be here to present, but he had an emergency and had to travel today. I'll give a little background on him. Anyway, he's a professor of mechanical and civil engineering at the Florida Institute of Technology. He leads the Wind and Hurricane Impact Research Laboratory at Florida Tech, and his research interests include risk modeling with applications to vulnerability of civil infrastructure, to hurricane wind, rain, and storm surge, and development and deployment of instrumentation for laboratory and field characterization of wind structure interactions. He's one of the lead developers of the engineering component of the Florida Public Hurricane Loss Model. Professor Pinelli is also a co-PI on the DesignSafe project. Also with us today is Sandarya Surihar. And Sandarya has a Master's of Science in Aerospace Engineering from Florida Tech and is working on experimental fluid dynamics. And we also have Dr. Mani Subramanian with us here today. And I think at this time, I'll hand it over. And well, I will say that Charlie Day usually does the introductions. I'm Scott Brandenburg, professor at UCLA. Charlie's having some technical difficulty, so I'll do the introduction, and then hopefully Charlie will be here to provide the link to the survey at the end of the webinar. You'll all receive an email with that survey link. And I think at this time I'll welcome, I think Sandarya, you're going to share your screen, and Manny, you can please maybe introduce yourself briefly and share with us. Thanks a lot for being here to fill in for John Paul last minute too. I know that it's a last minute request for you.
Thank you, Scott. I appreciate it. Thank you. Good afternoon, everybody. As Dr. Brandenburg mentioned, I am Chalakara Subramanian, aka Mani Subramanian. I am a professor at Florida Institute of Technology in aerospace engineering. My research interests are aerodynamics, hydrodynamics, fluid dynamics, and also wind engineering. I've been collaborating with Dr. Pinelli for the last 20 years on the wind engineering project. My contribution in the project is to do with sensor development, sensor deployment, data collection, data acquisition, and analysis of the data. So this presentation is going to be how we can use the DesignSafe features for data acquisition, data analysis, and also data presentations and publication. So I'm sure most of the audience will be interested in this topic. So we would like to share with you our experience, and particularly with reference to two of the experimentation that we did. One is a field measurement, the other one is a wall of wind measurement. So this presentation is going to be made by myself and Ms. Sandarya Sridhar, who will be talking more about the DesignSafe, Jupyter, TAPIS, and so on. I'll just talk about the experimental setup and the instrumentation. So this we both are going to share the presentation here. So this project is funded by NIST under the Disaster Relief Investigation Award. Can we move to the next one, please? So the outline of the presentation is significance and objective of the research project, data challenges, and then Jupyter and TAPIS workflow, DesignSafe workspace, and TAPIS data acquisition in quasi-real time, and how to create Jupyter notebooks for data processing and data visualization, then some updates on notebook, then project resources, and finally, I'll do the conclusion. And it will be followed by a very brief demonstration of the tutorial type. And this is what we plan to do. We hope to cover this in about an hour. So this project is titled, the research project is titled Characterization of Strong Wind Loads on Non-Structural Components. As I said, this is the research funded by NIST. We have been working on this. This is our third year of the project. Before that, we have been working on NSF funded project for also 3 to 4 years. And we had some Florida state funding for a number of years to develop our instrumentation and deployment of the instrument during different hurricanes. So the main objective of the research project is to understand the effect of strong wind events on non-structural components of residential structures. So there have been many studies, both experimental studies as well as analytical studies or numerical studies of wind effects on buildings. So this is to do with more of full-scale measurement, because as you may know, most of the laboratory studies are done on scaled models, and then there are some severe effects due to hurricanes which the models cannot resolve properly. Therefore, there is a shortcoming in the model codes and designs. That's what we found out. So this has to do with full scale measurements, and therefore we developed this instrumentation system. So NIST is interested in characterizing the pressure loads on components which are called non-structural elements of the building, such as the soffit and fascia, and also the windows and doors, and also the shutters, and including even the solar panels. Some of the homes, they have solar panels. So all these structurals, they are also subjected to high wind loads during hurricanes. And sometimes these components, they are not designed to engineering standards. So therefore, they tend to fail first, and then the failure propagates to other parts of the structure. So this is the reason why we are trying to collect some data, some real natural data, and to develop models or modify the existing codes which exist in ASCE 7 to be able to design these components to a stronger specifications. So the goal is to provide some measurement data. Next one, please. So we did some deployment, and when Soundarya presents the data collection and the data analysis, it will be pertaining to the deployments that we did. And the one is the field one, which is on the left, you see. In fact, both are field. This is a house in Satellite Beach, which is on the east coast of Florida. And we do deployment for both landfalling hurricanes and the hurricanes which are moving along the coast. And Florida being the most famous for hurricanes. We get many hurricanes, not all of them make the landfall, but yet we can study the characteristic of hurricanes and their impact on structures. So this typical deployment consists of pressure sensors, and our contribution, the FIT contribution to this research is we developed the wireless sensor. We are the first ones to develop the wireless sensors, which gives more flexibility in terms of mobility, carrying the sensors and deploying on different houses. And then the idea is to collect the pressure variations on the roof over the duration of the hurricanes. Typically, we collect data for at least 2 to 3 days, and this is the continuous data acquisition. And the sensors which you see there, they are like the white saucers on the roof, you see, and they have the electronics and also the transducer inside, and we can measure pressure and also temperature with the electronic sensors inside, and then they are wirelessly communicated to the local computer, and the data is then collected and stored both in the computer and also in the cloud. And now we are also working on transferring that data in quasi real time to DesignSafe, and we can actually analyze also the data on DesignSafe, and we can visualize what is happening. So as the hurricane happens, it may not be instantaneous. There may be a slight, like 5 to 10 minutes delay after the event really happens on the house, but we can see the pressure distribution. There is also, you see, an anemometer which is located on the top of the roof ridge line, and then we also place some sensors which are either this wireless sensor in the form of discs, or we use patches which are pressure tabs placed on a small aluminum disc, which are smaller in footprint compared to the ones you see on the roof. So on the right hand side figure, this is a test we did in the wall of wind at FSU in Miami. And so here we are comparing the data collected by our wireless sensor with respect to the ScanEval, which is used by the Florida International University for their wall of wind test. So we are comparing the two sensors, and this test is all about the sliding doors, the patio doors, for example. So this is one of our deployments. Next one, please. So this is the field one. You saw the picture of the sensors on the roof. So the same house is in Satellite Beach. It is about, I think, 1.5 kilometers or so from the coast, from the water line. And then you, actually it's less, I'm sorry, it says 0.37 kilometers right there. So, and then we have on that roof an anemometer, and we are also doing in parallel with this study the effect of the local roughness, the terrain roughness. So there is, we also use LiDARs and what we call twig nets. Those are all mobile anemometers and pressure gauges and humidity and temperature gauges, which can be located in any neighborhood of the measurement point around the house, so that we can also analyze the approach roughness on the wind field due to the approaching wind and how they affect the local pressure distribution. So this particular picture, the figure on the right, shows the track of the ASCE storm, for which we collected some data and implemented the DesignSafe features. So this shows the track. It did not make the landfall, as you can see. Our location in Satellite Beach is shown by this dot here, but this was the track of the hurricane. So we were, I think the closest we were about, I think it was 40 miles off the coast, but we did have some strong gusty winds. So we were able to get some characteristics, some impact of that. So next one, please. Now, as far as the data collection and data analysis goes, we encountered some challenges, and we would like to share them with you, because these field measurements and also the wall of wind measurements, they are all have some unexpected kinks. So therefore, we would like to just make you aware of that. So one of the things we came across was, since we use different types of instruments, for example, for measuring the pressure, we use absolute pressure gauges, and then there were some relative or differential pressure gauges used by FIU. So when we were comparing the two measurement, we have to take into consideration the effect of absolute pressure gauge versus the differential pressure gauge. And also we used differential sampling rates. Our sensors were sampled at 10 hertz, whereas the scanning valve was sampled at 520 hertz. Probably that's oversampling, but that's the rate at which the FIU were collecting data. And then we have some sensors like the anemometer, which sampled at 1 hertz. So we have different sensors which operate at different frequency response or sampling frequencies, and also the range of the data. They were all different. So you got to arrange the formatting of the data and data collection process carefully so that you do not lose any valuable information. The second aspect was the size of the data. So depending on the number of days we deploy, some hurricanes we deployed for 2 days, some we deployed as much as 4 days. So we start well before the hurricane approaches. So that is a day before the hurricane, the day of the landfall or proximity of the hurricane, then we continue with the next 1 or 2 more days. So typically our sensors, wireless sensors, can work on one charge for between 60 to 70 hours, and then we may have to recharge them. We are also implementing some solar charging so that we can stretch the duration of the data acquisition. So data set is one problem, and also the data structures. So these are some of the things that our program has to deal with. And since if you are gathering data from multiple data collection points and different instruments are used, then we have to coordinate the way the data has been sent back and forth and things like that. Then, of course, we have to always in the field measurement, particularly in the wireless measurement, you are likely to have some noise because, even if our system is noise-free, we also share the communication link, Wi-Fi links and all that, which cannot be guaranteed to be noise-free. So there will be some contaminations due to communication problems. We may have extraneous noise. So we have to clean up the data always. And comparison, and this is calibration studies. So we have to have a benchmark data to compare in situ and prior to the deployment about our sensors, because we have to establish the validity and the accuracy of our sensor during each measurement. So we do that. Then visualization of variety of metrics and analysis outputs. So again, this varies from one measurement to another measurement, or one experiment to another experiment. So we should have some flexibility of our presentation and visualization. Lastly, publication and accessibility to facilitate data sharing and reuse. So these are not really a challenges, but some of the things that we have to work through when we implement this DesignSafe analysis system. Okay, so this is the Jupyter TAPIS workflow diagram. So the first block, the block on the right, on the left, shows about the data acquisition part. Then when we go to the right-hand side block, it will be all data collection, data capture, and data analysis. So in the left-hand side, the bottom left-hand side block is the data acquisition sensors, which includes different forms of sensor, which I mentioned, the dish pressure sensor, the anemometer. The other one you see on a pole, that is called the pressure sensor, that is a reference pressure. Normally it is placed in a place where there is no wind effects, in a backyard or in an enclosed place. And this is for the reference pressure measurement. And the small disc you see with a long tube, that is the pressure patch. So that we use for small area, like on a fascia or on a vertical wall or a glass window, for which instead of putting that large pressure sensor, we use this small pressure sensor, which is called pressure patch really. And we can attach and remove it easily. And then it is connected to the wireless box, which all our sensors works wirelessly. There may be a small length of wire between the sensor control box and the transmitter, but that is not more than 1 foot long. Then that raw data is collected in a laptop, and so there is a local laptop at the place of deployment. Typically for field deployment, we can use up to 30 sensors, which includes all this disk type, and also the patch type. With anemometers, we can have more than one anemometer, and reference pressure gauge. We can add to this other things like GPS system, or we can put humidity meter, and rain gauge meters and things like that. So our wireless sensor system is designed for multiple types of data acquisition. So all this data is then stored in a particular format in the laptop. And so always the laptop will have the data, whatever data we collect. And unless we lose the laptop, our data is secured in there. And then we try to use the wide area network Wi-Fi system to communicate to the cloud, and including the DesignSafe. So what you see, if the DesignSafe has any communication problem, in some of the deployments, field deployments, we experience some connection problem to the DesignSafe. So as a backup, we have this private cloud service called Box or Google Drive. You can use any of that, where we can also upload the data and store it. So we have, two places where we save the data. We don't want to lose the valuable data. So that's the idea. Now, but if the DesignSafe connection is successful, we can move the data directly to the DesignSafe. And within the DesignSafe, we have created different functions through Jupyter notebooks. So you see that notebook 1, 2, and 3. So that does 3 different operations. Notebook 1 does the standardization of the information. What that means is the raw data comes in digital form, because most of our communication and the data acquisition is digitized and digital form. So we have to convert the digital form into analog form, and also we get the data for all the sensors in a long format, continuous format. So we had to separate the individual data for each sensor with respect to the location and whatnot. So that's what the standardization of information means. And the second notebook does the further data processing and calibration. So for each sensor, we have a separate calibration file, which is incorporated in the notebook Python program, and that converts the digital data into physical data, depending on the calibration constants. And the third one is processing. You process the data, and some of the simple analysis we do in the notebook 3, like time series display of the data, and we can do some plotting, such as the plotting of the wind speed versus pressure distribution for any location on the roof or vertical wall or a component. So these features already have been developed and exist, and so Soundarya is going to show whether this can be adapted to other applications. So I guess this is my last slide showing the DesignSafe workspace. So it has got different menu options. So first one is a data depot. This is where you have to sign in and also create a directory so that all your data will go in there. And then this has tools and applications menu also, and recon portal. So this is from some of the deployments. So we also say in a real physical world where the data is coming from, and it has got some metadata information there. Okay, Soundarya, you want to take over from here?
Yes, thank you. Hi, good afternoon, everyone. I know this is after lunch for many of you, so I'm going to try and keep this as informational and interesting as possible. We had a really good introduction of how we use DesignSafe in our project, and then we also had some information on the tools and resources available on DesignSafe. So if you're someone who's new to DesignSafe and starting off, you have a data set and you want to kind of start with your analysis, my data is a more private or personal space to do that. And then if you are ready to start collaborating with your team members and even maybe publish a few of your work projects, or my projects is the place to go. And then there are others like community data and published projects where you will be all of the published data sets are free to access, and also they're curated for you, so it's easier to understand what other research teams in this community are doing. The tools and applications, the particular tool we use for our project is Jupyter, but there are others like AdCirc, OpenFOAM, and ANSYS. They're just some of the examples. And then, like Dr. Subramanian mentioned, there's Recon for reconnaissance data, and Learning Center for educational purposes. So they have videos, documentations, and even webinars. So that's just a summary of that previous slide. So jumping back into our project, if as many of you might remember, we have a network of wireless sensors that upload data to a local system. And then we need to, by quasi-real time, it means that we can fix an interval. So if I want, if we have deployed it on a field, and if I want my data to be uploaded every 5 minutes, how am I going to connect the local system to the DesignSafe is the question we're trying to answer here. So TAPIS is an open source application that allows you to do exactly that. And that is done by an access token. So I was planning to kind of shift to an exercise at the very end of the presentation, but I'm just going to quickly show you how we access TAPIS. So the requirements for using TAPIS is Python 3. You need to have the executable version of Python 3 downloaded to your local system, and then you can install TAPIS from there on. And the third one is the most obvious one, but we have run into issues with our Wi-Fi connections. So in a large facility like the Wall of Wind, there's going to be Wi-Fi interferences, and there's a bandwidth that we need to follow for a good Wi-Fi connection. So you need to have strong and continuous. 3G is good for residential areas, but then when you move on to more large-scale facilities, 4G is the is the recommended hotspot for your local system. The links that I have provided in the presentation will actually take you to either documentation. So this particular link on the right side is the link for documentation regarding TAPIS, and then Python 3 is the downloadable, the link where you can download Python. So let me escape from this presentation and quickly go to PowerShell. So accessing Tapis, you run it as an administrator. I hope I'm still sharing my screen. Let me just check if we have a quick, okay, no Q&A as of now. All right, so we have to add pip or PIP to the path. So this will work only if you have Python 3 installed on your system, right? And then after you add your path, you need to install Tapis. So I'm going to show you how to install. It's just PIP install Tapis CLI. Since it's already installed on my system, it's going to throw me a bunch of lines. But then after that, if you want to check if Tapis is already on your system, just type in Tapis and it should display. Move this. What is this button? Yeah, it should display Tapis. So now I can go in and access DesignSafe through this. So let's say auth init interactive. So that should take me to a list, and you can see DesignSafe. That's the location we are interested in. Apologize for my mediocre typing skills if you are like, how slow is she typing? DesignSafe, then my password. All right, did I enter my password correctly? I did. Okay, so for the registry URL, you can skip all of these steps. The main one is you need to get something called an access token, right? So once you're in this, it means that you'll be able to connect your local to DesignSafe. And the way to do it is pretty straightforward. You just have to say, you want to upload files right now. So it's just files upload. And then there's a syntax that you need to follow. I'm going to type in agave. So for today, I would like to upload something called a folder called Jupyter Workshop. And inside that folder, I have a raw data set example. And then we also have a Jupyter notebook. And it's this destination. So it's right here. And then we want to upload it to a design. So if I'm a new user to this, and if I want to start uploading it into my personal space, which is my data, all I have to do is copy this link right here. So after agave, whatever I have, I'm going to copy that, paste it into this, and then this is going to be your destination. And then you need to also mention what your source is. So I'm just going to copy this one right here. Go back to my, change a little bit of everything. So capital, it does not recognize capital letters. I close that. And hopefully that will upload my folder to DesignSafe. So we have to wait for a while here to see what it says. And there we go. To verify if it's really there, I'm gonna refresh. Usually with live demos. Yes. So we have the folder Jupyter Workshop, and like I mentioned, the raw data set as well as the Jupyter notebook. So this is the personal space, right? But then if you're really ready to start collaborating, and if you already have a project set up, instead of the link that I mentioned here, which says DesignSafe storage default, you'll be going to a project. Let me go to Isaias and then copy this particular link, right, to connect your Tapis. So going back to the presentation, this was a success. So I'm happy about that. Going back to the presentation, if you're interested in a quasi real time, so right now I showed you how to connect your local to your DesignSafe. But if you want to start uploading files in intervals, then you have to set up a program that's going to read new files in a specific folder all the time. So you go into PowerShell, you set up the token, and you upload, you run a program that's going to write and say, hey, if you find a new file, you need to start uploading it to DesignSafe and keep changing your source or the last part of the code line. So I hope that was easy to understand. So that is the quasi real-time or data uploading part. And then coming to the actual notebook. So once there's data on DesignSafe, we want to start looking at the numbers. And because these are all raw data, we want actual information from them. So there are 3 notebooks. The first notebook is for setting up the metadata or kind of describing what the file contains. So for every deployment, if we have a set of 20 sensors in the first deployment, the next deployment, we're going to have a completely different set of sensors. Sometimes the way we write the files might also change, like the columns might have switched, or the data formats, like the timestamp formats might have changed. So this notebook is going to take in that parameters, that set of parameters, and feed it into the next notebook. So the person who uses this is an experimentalist like me who wants to set it up, set up the deployment information. It is ideally used only once. So every time we go for a new experiment or a new deployment, I need to run this only once, and then that's it. The notebook 2 and 3 can be run multiple times. And the advantage to this is if there is any changes made to how we store the data, or if there are any changes in the data format or the sensor numbers, or even missing instruments, like if we don't have an anemometer, then that's going to account for all of that. So an example of how this parameter looks, it should be appearing right now. Okay, is on the right side. So those are the parameters that we found was most important for data processing. And that's the sort of information that it'll collect here. So again, I can quickly jump out of the presentation and I'll show you one of our published projects. So to access that, you go to Workspace, Data Depot, and under Data Depot, you go to Published. And if you type in wireless, all the 3 published projects are actually our team's projects, so you can access any of it and find out the Jupyter notebooks. And it's curated in such a way that this particular project is related to wall of wind experiments, and it's curated in such a way where you can find the manuals, the Jupyter notebooks, and also the different types of sensor data very easily. Since we are talking about notebooks as of now, I'll go into the notebooks, and it's labeled notebook 1 standardization file, and click on open in Jupyter. So you have something like this, and if you run the first cell, so for anyone who's new to opening, if you have a design account, and if you're new DesignSafe account, and you're new to opening a Jupyter notebook, then you would want to start your server. And at the end of executing your notebook, you just have to go to control panel and stop your server. So moving on, I ran the first cell. This is the default data that we have, right? So if you want to change anything like the sensor numbers or the anemometer, you can just follow the bookmarks and enter whatever sensor number you want. So say my experiment has 70 to 95, and then I also have like 101 as my sensor, and then I actually don't have any anemometer, or I do have, and it's called 21 this time. So once I'm done with all of that, I can go back to writing all of the information. And if I run this, it will reflect all the new information that we wrote down, and it'll be ready to move on to the next. So I don't want to save the file, so I'm clicking on no, but it'll write down a metadata file, and it'll you'll be able to feed this into your next program. So that's where the second notebook comes in. Second notebook is mainly for calibration and organizing the data. Initially, we'll have a lot of CSV files, and because we are uploading every 2 to 5 minutes, and this is a 10 Hz sampling rate we are talking about, there'll be about 100 files or more. Dr. Subramanian did mention that it can even go up to 1 GB sometimes. So we use pandas data frames mainly for storing these files, and we store them as data frame objects, and that's called a pickle. So data processing is done whenever there is new data uploaded to the same experiment. So once I set up the metadata file, every time, for example, in a quasi-real-time situation, if I want to check how my data looks every 1 hour, then I'll have to go and run the processing notebook every hour, because I'm sure there's new data being uploaded to DesignSafe from time to time. The objective of the script is to read the raw data files, organize them, apply the calibration constants, and then save them as either data frame objects or CSV files, so that we can pass it on to other research teams that might be interested in looking at our data. So that is just a summary of what the Notebook 2 does. And the Notebook 2 is very straightforward when it comes to running. So it's not user interactive at all. All it does is it reads the metadata file, reads the raw data, and then applies the calibration. And we have a separate file for the calibration constants, right? And you just need to hit run, and the notebook runs the script and throws out your information. So the most interesting part is Notebook 3. Finally, when you have done all of this hard work, risking your life during the deployment, we come to Notebook 3, which gives you the actual information of what happened at the site or at the experimental facility. So the way we make it interactive is by providing drop-down options, or even sometimes animation frames. There are two ways to go about an animation frame, right? So we can either mesh the values and kind of show averaged values along that area. But then when you really want to see how your sensor is performing, instead of having like a timeline series, if you're able to see all of the sensor values at a shot based on the location, then I think an animation frame is a great way to go about it. So we'll be seeing a little bit of Plotly as well. And I do have an exercise. If we have the time to cover it, I'll be more than happy to demo that for you. So again, the type of user here is an analyst. So it doesn't have to be me. Dr. Subramanian wants to look at the test results, I'll set it up for him. I'll make sure that the notebook is working, and all he has to do is go inside, run the notebook, and he'll be able to see some results. So instead of showing you like a static picture, let me jump into this again. And every time you want to close your notebook, this is for people who are new to Jupyter Notebook, leave. I'm going to go to interactive analysis. Again, I don't have to show you processing because everything I do is just hit run and it plays. So this is for one experiment, which was a glass sliding door experiment. And the advantage of using a Jupyter notebook is there are different types. You can either have them as a markdown or a script that you can run. So it's literally like a notebook. It's easier to understand. You don't have to have a separate documentation to explain how to use the notebook. So we've tried to cover as much as possible for anyone who's new, and they'll be able to understand this quickly. This explains the setup of the experiment, some important information like what were the different wind speeds and the angles that were used, what is the dimension, because that's an important number that we need to know for the ASCE calculations. And it says during the first run of the notebook, you need to go to kernel, restart, and run all. So I'm going to do exactly that. And if you're new to Jupyter, again, every time you start a server, you might have to install a few packages or libraries. So that information is also provided here. You might have to change back and forth between Markdown and code to enable that. Since there were different wind speeds, I'm just going to go ahead and choose the highest wind speed available, which is 105 miles per hour. Wait for a bit, and okay. And then it shows you an animation frame. So this is the Plotly that I was talking about. If I mesh this and gave you average values, you wouldn't be able to understand what each of the sensors read. So this is a good way to kind of toggle between different wind directions. So since we had only 3 wind directions in this case, we have 3, but if you have more variables, you can kind of expand this animation to fit anything you want to study. So in this case, you can see that with 0 degree, which is the headwind direction, it's directly hitting your glass door. It has a higher CP value. And then as it becomes more cornering, because of the interaction of the fluid and then the different boundary layers, and also look based on the height it's set up at, it's reading completely different CP values when you compare the right and the left side of the door. So that is just an example of the notebook. And then coming down, it doesn't stop there. It also gives you some option, and the type of analysis really differs from one to the other. And we have a few other notebooks that have been published, but the menu is not the same for everything, but the functionality is almost similar. So for this one, I have, oh, I accidentally turned it into Markdown. I'll write down CP plot, and it asks me to write down, I need to follow a particular format like sensor, tap number, wind speed. And for glass sliders, the interesting point is we wanted to compare the loads when you have a shutter and when you don't have a shutter. So what is the role of a shutter playing in the hurricane, and how significantly does it reduce? I'm going to take sensor here, which is 79, and run it at 105 miles per hour for maybe 45 degree. And let me do 0. And then I don't want the shutter for this case. Make my life simpler with copy pasting. And say the second condition is I want it with the shutter, and then maybe compare it with this with the value from the right side of the door. Say I want 8. One more, bear with me. One, and then if I want to stop the analysis, I hit 0. And then it throws it gives me a plot, right? So this is again a plotly plot. A lot of people are more familiar with matplotlib, but we are mainly using plotly for most of our analysis work. So we have 79, which was on the left side of the door, 8 on the right side, glass sliding door. And then it also tells you if there's with or without. So let me switch off the right side doors and look at just the left. You can see that when there's a shutter, the pressure coefficient drops. And then if you compare without the shutter for the left side and the right side, you have another value. It says my internet connection is unstable. I'm just hoping that you guys are receiving whatever I'm saying.
Broke up for a minute. You're good, Sundarya. Yeah,
okay.
We can hear you.
And then there's a table in the end that kind of displays what the minimum, maximum, mean measured measurements were. So if I want to play this again, if I want to go to another option, I just have to unhide these cells and play just the main menu now. I don't have to run the whole program every time. And this is a Cobra probe data, which shows you what the actual measured velocity was during every test condition. We thought this would be an important information to show, and that's why we included it. So this is just one example of our analysis notebook, but we do have other notebooks with other options available. And moving forward, the slides are going to be in the same tone. So this is for the glass sliding doors with and without shutters. Some of the why you saw a huge difference in the pressure coefficient values were also because of the fact that the glass was recessed behind the wooden panel. And all of that information, we try to cover as much of it as possible in the markdown. So this is the animation frame for the glass sliding door. Since I've already shown it to you, let's just move on to the next. And then this is exactly describing that sort of flow where you have different boundary layer effects. The glass panel being recessed behind the wooden panel is showing you a different, a significant difference in the CP values. Then the most interesting cases being cornering wind flow, right? So apart from the glass sliding door test that I spoke of, we have also had multiple wall of wind experiments for different test models. So this particular model is has two pairs of glass sliders. So this is one surface, and then at the back of it, there's another surface, and we do it in different wind directions. So this is one animation. And then if you go below, that's another test model, and we call it the fascia and soffit test because we had the patches on the fascia and the sensors with casing on the soffit. And then depending on how it's aligned, we kind of try and align your plotly animation to the same and have them display. And you can see it's very small, I know, but since there are different angles available, more than 3, we have a bigger scale, and you can see how it acts in different directions. So you see how the CP, as it becomes more and more orange, it means that there is higher CP. So as the wind direction changes, you can really see that. And it's some of the interesting information to take away from this is one side is a hip, the other side is a gable. So sometimes there's effect of the type of roof as well. And then this is the field test. So whatever I spoke about before was an experimental. Now we're moving to the field test. And field test is very different from an experimental test because we have interaction with surroundings and they are not done at a uniform flow condition. We really just leave it to nature. So we have changing wind speeds, changing wind directions, and also the roughness surrounding that area. And it's definitely more interesting to study a field test because you have the effect of gusts on residential houses. And there is a difference between the effect of non-structural components when you keep it in an actual house as compared to a test model. So this is another animation frame with respect to the field experiment. And one way, when you have this as a quasi real time and when you have this analysis run, say every hour, you'll be able to see important information like whether any sensor was not reading data. So for example, if I go back and forth, you can see sensor number 3 come into the picture, which means sensor 3 was not collecting information for a while, and then it comes back online. And then there were windows when some of the sensors went black. So the black means that they were not reading any data. And if you compare it to the color legend or the color scale on the right side, you see there is no black, which means there was no data being collected. So at these windows, if I'm operating it, and since it's quasi real time, I can sit and look at it from my house. And if I see that it's not collecting, I can immediately email my team members and ask them to go to the site and fix the wireless sensors, or even discuss why it won't be working. So we can do all of that. And that brings us to the end of the analysis part. So we had 3 notebooks, if I have to summarize it again, 3 notebooks. The first to create metadata, the second to read in the metadata and calibrate it, and the third one being the main notebook that a lot of people are going to be using is for analysis. And the main point of this presentation was if you are dealing with a large data set which is similar to ours and you're collecting information, but you don't know where to start with your project, I think these notebooks are very adaptable. You can just take it up and you might have to do very few changes to the code or how you read in the data, but for most part of it, you will find very useful information in the processing as well as the analysis notebook. So the upcoming notebook updates is, I mentioned before that we create data frame objects and we use pandas data frames for a lot of the analysis. So we're planning to shift to database, and we've already tried out SQLite. It works perfectly well for our project. It's just that we don't have it uploaded to DesignSafe yet. So we're still in the testing phase where we're going to upload it to DesignSafe and see if everything is working perfectly. And also merge the analysis. So try to make the analysis very similar to Notebook 3. That's another thing that we are working on. And the advantage is to shift from a data frame structure to a database is there's faster data querying. 1 GB might not look like a large or big data for you, but when it comes to filtering or sorting through the data for smaller time windows, it takes a long time when you start using a data frame. And especially if you want to build up hundreds of CSV files or a million rows of data into a single pandas data frame, then that's going to take up a lot of time as well. And we had to request for extra memory for all of these operations from DesignSafe, and they were very helpful in fixing that issue with us. So the reason why we're moving to databases, we don't have to look into such issues. And secondly, it also is a relational database. So we don't have to create any documentation explaining what is the relationship between different files. And you're going to find all of the important data in one single or in a single .db file and not multiple CSV and pickle files. So yeah, project resources for this project, you'll be able to access information or publish data sets using these links. We have the field data example and the experimental. So the experimental is what I showed you right now. But for the field, it's from Isaias, and they have more options. So if you want to look into what we did, I would really recommend you to go into field or Isaias notebook and see what we've done with that. Lastly is documentation. So we are coming up with an introductory document to explain what we do, and it's all going to be on DesignSafe again. So we haven't published that, but it's in the process. I think I'll hand it over to Dr. Subramanian now to.
Sure. Thank you. Thank you, Soundarya. Really good. Well done. Can you move to the next slide, please? Okay, so all left for me to do is to thank the National Institute of Standards and Technology for funding this project, and National Science Foundation who funded the DesignSafe activities. So we are very grateful to NSF as well. And FIU helped us a lot in wall of wind testing and shared their data for Scannival for comparing with our set of data. So we really acknowledge their help. Next slide, please. Okay, so to conclude, so we talked about the instrumentation and the field test and the wall of wind test, I should say, and how we can use the DesignSafe features for acquisition, quasi real time, and also store the data, process the data, and analyze the data. And we can do all this in quasi real time, because quasi in the sense between the time we collect the data, the time we visualize, it may be a matter of like 20 minutes, 25 minutes delay. But in terms of the hurricane life, that is not a big time, because generally the hurricane lasts for many days. So still we can get pretty good idea about what is it doing to the structure. This new feature, we are all excited because we can do large scale data analysis and processing. And so the DesignSafe is being expanded. They are adding new features and like high performance computing. So that will be an added bonus to doing the analysis and comparing with the field simulation, field data, or simulation of the field simulation data analysis we can do in parallel. So we are hoping to also engage in those kind of activities as the DesignSafe features are being enhanced. And of course, curation and publication is the main thing for our research. So this also provides that opportunity. curation, publication, and also sharing of the process data, raw data, results of the data, everything. So thank you. And if there are any questions, I think we went a little bit over the time limit, but we'll be happy to answer the questions.
All right, thanks very much, Manny and Sandaria. I do have one question. You mentioned that you're using SQLite to, help you with the file size, because my understanding is you just monitor these sensors at some high frequency, like all day or something, right? So the file size becomes very large. It looks like you're only getting out a small window of data to look at a time, right? So you don't actually need the entire data file. So I'm just curious about how moving from this big pandas data frame pickle file to a database will improve the performance of your Jupyter notebooks.
I think Soundarya can answer that. She has been doing that. We collect the data for a long period of time, as I said, because we don't know when the real interesting event will occur.
Yeah.
So we collect for many days, and then we will look at, we replay the data, so to speak, and identify the regions of interest where you have stormy situations, where you have short-term and long-term gusts and periodic gusts and things like that. And then we analyze the other data around that time. So she has built up some features into Notebook where we can specify the start time and end time, and in a big lengthy data set. Do you want to add anything to that, Soundarya?
Yeah, sure. So yeah, going along the same lines of what Dr. Subramanian said, even though we deployed for a long period and maybe just a small window is our window of interest, we do have to look out for all of how these sensors are performing, because we're actually not on site, and everything kind of relies on the connection between the local system to the sensors. So sometimes the sensors might not be communicating properly. And if all of this information can be uploaded and visualized or even studied from time to time, it'll help us maintain that connection with the sensors. And also, after all of it, or after the deployment is done, we can cut it down to a smaller chunk of time. We'll have to study that, though, to understand what the windows of interest are.
Yeah. I think it's a common problem. This is a problem we have. I'm an earthquake engineer, and we actually record ground motions at 200 hertz all day, all the time, continuously.
Yeah.
And when an earthquake happens, it may only last for 40 seconds, right? And we want to get that 40 seconds. So I think it's a common problem. So I'm interested to see your.
Yes, and you use
approach.
databases as well. So it's, when I've seen you query data, it comes in easier. Whereas with Pandas data frame, sometimes I'm just sitting there for a few minutes, wondering if it's gonna jump into an error or if it's actually working. So databases is a quicker way for us to navigate this issue.
Yeah, and then you end up with a manageable size Pandas data frame, much smaller than a gigabyte or something like that, which makes it a challenge.
Yeah.
That is
and
true.
ours is a static database compared to your more dynamic, like we just upload data once, and after the deployment it's done, move on to the next database. Whereas I guess you're uploading to the same database, right?
Yeah, ours is constantly changing. So that's that makes it fun. It's hard to manage that too. Anyway, we are a little bit over time. I don't see any questions, so maybe I'll hand it off to Charlie, who I think has overcome his technical problems to be with us here at the end of the webinar. So Charlie, it's all yours.
Thank you.
Thank you.
Hey, and thank you so much. Actually, it was a great presentation, and I'm a huge fan of using Plotly, so it's great to see that in an application. Plotly is awesome, and I'd like to see more people using it, to be quite honest.
I agree with you. Yeah, it looks nice.
Share here. All right, so everyone should be able to see my screen, I hope. So, all right, so thanks so much for your presentation, everyone. I really appreciate you being here and taking the time to present your work for the DesignSafe community. For anybody who wishes to see these and other webinars we've done in the past, we do have a training archive. If you go to DesignSafe and click on the Learning Center and go to training, you'll see all of our previous webinars and a link to our YouTube channel, so you can watch them all over there as well. Finally, everyone who's still here, if you could please click on and take a picture of this QR code. This will take you to a survey, so we can give us a little bit of feedback on today's presentation and give us some information on what you'd like to see for future presentations, so we can basically bring you what you want to see and when you want to see it. So we really appreciate if you can give us some feedback. That really helps us design and put together these webinars for you. And finally, special thank you to everybody involved in today's presentation. I know Jean-Paul wasn't able to be here, but we appreciate your stand-in. Thank you very much, Dr. Subramanian.
You're welcome.
And Sandara, great presentation. We really enjoyed your talk and really enjoyed looking at the notebooks and seeing how your workflow actually fits. And I'm sure the community was excited to hear that too. If anybody has any questions out after this webinar, feel free to hit us up on Slack or shoot us an email, and we'll make sure that the presenters get your questions to them. So once again, thank you very much. Thank you very much, Scott, for stepping in and emceeing this today. And we'll see you all next time. Thank you.
Thank you very much. Have a nice evening.
Yeah, have a great afternoon, everyone.
Yeah.
Everybody.
Thank you. Bye.
So because I had gotten cut off, it won't let me stop the recording. So we all just gonna have to leave.
Okay.
All right.
Thanks, Natalie.
All right.
Bye.
Bye.
Bye.